Hello everyone, welcome to Chem analysis. In today's lecture, I will be discussing a very important topic, that is the calculation of transition energy or corresponding wavelength for transition in case of conjugated pi electron system, and this pi electron system behaves as a particle in one-dimensional box, and for cyclic conjugated system where the pi electrons behaves as a particle in a ring. Now, if you are given a state chain pi electron system, that is like 1,3-butadiene, it is a conjugated system and can be seen as a state chain, that is a linear molecule, and the pi electron of this system behaves like a particle in one-dimensional box system. Now, in this case, if the pi electron behaves as a particle in one-dimensional box, then the wavelength corresponding to such system, psi n, will be root over 2 by L sin n pi x by L, and the energy corresponding to nth state will be En is equal similarly to the particle in one-dimensional box related system, 8mL square. Here n is the quantum number of the state, h is the Planck constant, m is the mass of electron. In this case, since the electron behaves as a particle, so m is the mass of the electron and L is the length of the conjugated pi system. Now, if you are given the length of the conjugated system, then it's fine, you will just put the value and you can calculate the energy of the corresponding nth state, and similarly you can calculate the transition energy, that is delta E will be Em minus En. If electron excites from nth state to mth state, then the transition energy will be like this, Em minus En, and the energy will be like this. Now, if you are not given the length of the conjugated system and you are only given the CC double bond length and CC single bond length, then you have to calculate the length of this conjugated system, and you can calculate it easily. Now, since the pi electrons is conjugated along this chain, the chain length will be extended on both sides to some extent, and it is observed that due to this conjugation like this, or similarly in the opposite direction like this, it is observed that the chain length increases at both sides, that is equal to half of the CC single bond length. Then the effective length of this conjugated system will be 2 CC double bond length, and here is one single bond, and since in each side half of the CC bond length increases due to conjugation, then in total in both sides half will increase, and in total there will be increase of 1 CC single bond length. That is, if you are given the value of C double bond C length and CC single bond length, then you can calculate the length of the conjugated system, like 2 into CC double bond length plus CC single bond length. And if you put the value of L in this equation, you can calculate the transition energy. And if you put the relation like this, hc by lambda in place of energy, then you can calculate the corresponding transition wavelength. Is it clear? Now, if you are given a conjugated cyclic system, like just suppose benzene, in this case the electrons behaves as a particle in a ring. Since the electrons are conjugated within a cyclic system, that is within a ring, the pi electrons behaves as a particle in a ring. In such cases, the wavelength corresponding to nth state is equal to psi n is equal to root over 1 by root over 2 pi into e to the power plus minus I n theta, and the energy corresponding to nth state is equal to n square h cross square by 2I. I is the moment of inertia, and in place of I, and if we substitute h cross is equal to h by 2 pi, and I is equal to m r square. M is the mass of the electron and r is the radius of the conjugated cyclic system, that is radius of the benzene nucleus. Then it will be n square h square by 4 pi square and 2, that is 8 pi square m r square. Now if all the values are given, then we can calculate the energy of the nth state and the corresponding transition energy from nth state to mth state. It is also very easy. If you just know the formula, then you can easily calculate the corresponding transition energy and similarly corresponding wavelength for the transition. Here I want to mention one thing. The value of n in this equation is n is equal to 0 plus minus 1 plus minus 2. That is, here I want to mention one important thing, that is the energy state for n is greater than 0 are degenerate state. Since if we put the value n is equal to plus 1 and n is equal to minus 1, we will get the same energy value. That means two different energy states having the same energy value, that means both the states are degenerate. That is, for n is greater than 0 states are degenerates. And for a specific value of n, there will be 2n plus 1 number of energy states. For benzene, the value of n, maximum value of n is equal to 2, and for that there will be 2 into 2 plus 1, that is 5 energy states. For benzene, since n is equal to 2, there will be 5 energy states, and energy states are like this, that is 1 pi for which n is equal to 0, and 2 pi for which n will be 1, and that is n will be plus minus 1, and the two energy states will be degenerate, and for n is equal to plus minus 2, that is the energy states will be similarly will be degenerate. And if we put the 6 electrons in this energy states, the orientation will be like this. And if we want to calculate the transition energy, the electrons will be excited from n is equal to plus minus 1 to n is equal to plus minus 2. That means the energy will be 2 square minus 1 square into h square divided by 8 pi square m r square. Is it okay? Now we can calculate also the corresponding wavelength corresponding to this transition. Now in case of naphthalene, the n value is 3, and similarly there will be 7 energy states, 2 into 3 plus 1, that is 7, and the energy states are oriented like this. N is equal to 0, n is equal to plus minus 1, n is equal to plus minus 2, it is n is equal to plus minus 3. It is 1 pi, it is 2 pi, it is 3 pi, it is 4 pi. And since in naphthalene there is 10 conjugated electrons, they will be distributed like this. And if we want to calculate the transition energy, we can calculate it easily putting m is equal to 3 and n is equal to 2 and using this expression. It is for naphthalene. Now let's see some questions related to this topic. Now this question came in GATE 2017 for 2 marks. It is given that assume 135 hexatriene 135 hexatriene to be a linear molecule and model the pi electrons as a particle in one-dimensional box of length 0.79, that is L is equal to 0.70 nanometer. The wavelength in nanometer corresponding to the transition from ground state to the first excited state. Now the energy expression, as I have discussed at the first of this topic, that is n square h square divided by 8 ml square. L is given here, m we know the energy, we know the mass of a electron, and h Planck constant we know, and here we have to know the value of n. For the ground state of 135 triene, the energy of the different state is like this. It is n is equal to 1, is 2, 3, 4, 5 and 6. Since there is 6 carbon atom, there will be 6 energy state, and in 135 hexatriene there is 6 electron, that is the n value for the ground state is equal to 3, and for the first excited state it is equal to 4, that is m is equal to 4. The electrons excited from n is equal to 3 to n equal to 4. That is, if we put the value here, we can calculate the corresponding wavelength for this electronic transition. That is, in place of En I am writing hc by lambda. It will be 4 square minus 3 square into h square divided by 8 m l square. H on h will be cancelled out, and lambda will be 8 into m, that is value of m is equal to 9.1 10 to the minus 31 kg. Value of L is given, that 0.70 nanometer square, and it will be c, that is velocity of light 3 into 10 to the 8 meter per second, divided by 4 square is 16 minus 9, that is 7 into h, that is 6.62 into 10 to the power minus 34 joule second. It will be 9.1 10 to the minus 30 into point. If we transform this nanometer to meter, then we have to multiply it with 10 to the minus 9, that is it will be 7 into 10 to the power minus 9 square, 3 into 10 to the power 8, it is meter cube per second, and here is 1 kg per meter cube by second. It is 7 into 6.62 into 10 to the power minus 34 joule into second. Here we can transform this joule into kg meter square into second to the minus 2, that is kg meter square per second square. And if we cancel out the unit, then kg will be cancelled out, meter square and meter cube will be cancelled out, it will be only meter. And here is second inverse, here second and second it will be second inverse. So second inverse will be cancelled out. The unit of this calculation will be meter. Now if we calculate this whole value, you will get the calculation will be 230 into 10 to the minus 9 meter. That is, we can write it as 230 nanometer. That means the wavelength for the corresponding transition is equal to 230 nanometer. You just check the calculation, it is right or wrong. Sir, is this or something near about this value? So let's see the next question. This question came in GATE 2018 for 2 marks. It is given that the pi electrons of benzene can be modeled as a particle in a ring that follow Pauli's exclusion principle. Given that the radius of the benzene ring is 1.4 angstrom, we have to calculate the longest wavelength of light that is absorbed during an electronic transition in benzene. Longest wavelength, that means the energy corresponding to electronic transition will be shortest. Now in case of benzene, as I have discussed at the beginning of this lecture, that the HOMO corresponding to n is equal to 1 and the LUMO corresponding to n is equal to 2, and the electronic transition corresponding to n is equal to 1 to n equal to 2 will corresponds to highest wavelength, that is lowest energy. Since if electron excited from n is equal to 1, n is equal to 0 to n equal to 2, then the corresponding transition energy will be higher and the wavelength will be lower than that of n is equal to 1 to n equal to 2. So we have to calculate the wavelength corresponding to n equal to 1 to n is equal to 2 electronic transition. Now if we use this expression for calculation of energy, that is E delta E will be m square minus n square into a square divided by 8 pi square m r square. There is, in place of delta E or E, we can put hc by lambda, and here m is equal to 2, that means 2 square 4, and n is equal to 1 to 2 electronic transition, it is 1, and it is h square divided by 8 pi square m r square. H will be cancelled out, so lambda will be lambda will be 8 into pi square into m, value of m is equal to 9.1 into 10 to the minus 31 kg. R is given as 1.4 Armstrong, 1.4 into 10 to the power minus 10 meter. Is it okay? 1 Armstrong is equal to 1 into 10 to the power minus 10 meter. Its square into C, it is 3 into 10 to the power 8 meter per second, and value of H, that is 3 into 6 into 62 into 10 to the power minus 34 joule second. In place of joule we can write kg meter square second to the power minus 2 into second. That means if we calculate the unit, then as previously it will be kg will be cancelled out, meter square and this meter square will be cancelled out, and second inverse, it will be second inverse, and it is 1 by second, that is second inverse. This all will be cancelled out, so the unit will be only meter. Here I want to mention one thing, that only meter square is cancelled out, not the this part. This will be meter, this will be square, and if we bring the unit at the outside of the bracket, then it will come out as meter square, and this meter square will be cancelled out, and the whole unit will be in meter. So if you calculate this whole term, then you can see that the value will be 212 into 10 to the power minus 9 meter. That means 212 nanometer. So the longest wavelength corresponding to this electronic transition for benzene is 212 nanometer. It is near about 210 to 215. Just check the calculation once. So that's all for this lecture. If you like this discussion, then please share it and please subscribe to my channel, because your support will help us and will motivate us to make such interesting videos in future. So please subscribe my channel. Thank you.